Hello and welcome. You might be tempted at some point, especially when you're in the middle of taking a math class. Why is it that we math teachers love this stuff so much? Why is it that we would spend our lives working with this stuff, teaching this stuff, exploring this stuff, learning this stuff, basically living it out? What is it that we love so much about this? Well, you might be surprised at what the answer is, and the answer becomes more and more apparent as we start to get out of the area of arithmetic and calculation and start to get more and more into the realm of algebra and equations. Because when we start to get into the world of algebra, you might be surprised to find out that math actually becomes less and less about numbers. Let me say that again. When we start to get into the realm of algebra, math becomes less and less about numbers. Math at this level is actually about patterns and relationships, the ways in which we can describe patterns in nature and patterns in our culture, relationships between different quantities, different things that interact with each other, different things that go up as others go up and go down as others go down, or even opposite to that, going up as other things go down and go down as other things go up. There are relationships that exist between quantities in our culture, in our economy, in our ecology, in our astronomy, in our physics, in our engineering, in all aspects of our life. The process of studying, being able to quantify these things, being able to understand them and explore them, manipulate them, I got to tell you, after a while, there's a tingling in the spine, a sense of being reminded of just how complex our world is and how, in the realm of our universe as a whole, everything is ultimately connected. We're going to start to take a look at how we describe some of these patterns and relationships as we start to explore more and more how we solve equations. Really all we're doing is we're working with those relationships. We're manipulating those patterns in a way that can serve our needs. So let me first of all take us to a point where we can take some time for ourselves here to become completely attuned to the present moment. Take some time for that. Welcome back. One of the first vocabulary items that you might have heard at some point in the area of algebra is the concept of the term. It's one of the items that exists oftentimes in algebraic expressions. What exactly is a term? Well, to explain that, let's start talking again about the order of operations here. Now, I'm showing you an expression here that involves some numbers, and it starts with -8 times 2 to the third power plus 7 times 5 minus 40. And there's a lot of different mathematical operations that are present here. And which things are done first? Well, we do parentheses first, and there are some parentheses there, but they're not really, nothing is really going on inside any of those parentheses, so we're free to move on to exponents. And there is an exponent there, 2 to the third power, that's 8, so we'd evaluate that first. And then we'd start to do the multiplication, multiplying that 8 times the negative 8. Oh, and there's also a multiplication to take care of between the 7 and the 5 as well. And it's only after all of those things are done that we would finally do the addition and subtraction that separates this, that really separates this expression into 3 different parts. You see that? So we'd have the first part of it would be negative 64. The second part of it would be 7 times 5, which is 35. We'd add those things together. And then lastly, we'd have minus 40. We'd have to subtract that off. Next, I want you to go back to our onion picture, our onion analogy, and see that this is actually an onion that has 3 separate centers to it. One farthest to the left, one in the middle with that 7 times 5, and one at the end there with the minus 40. So each one of those things contains a set of operations that has to be done first before you can put all those things together with addition and subtraction. Those things that you have to that have to be done prior to the addition and subtraction define what are terms. So the first term here is the negative 8 times 2 to the 3rd power. That's our first term. The second term is 7 times 5. That's the one in the middle. And the last term there is negative 40. And it's only after all of those things are done that order of operations says that we can then do the addition and subtraction. So there's really 3 parts to this, like an onion with 3 centers to it. Maybe it's a garlic clove or something that's got 3 different centers to it. This is also true if we're dealing not just with numbers, but also with variables. This is a set of 3 terms here once again, even though what we're dealing here is with an x and a y instead of just numbers. We still have a negative 8 multiplied by that x cubed. It's only that x that's getting raised to that 3rd power there. All of that has to be done before we can do addition and subtraction there. We also have to take care of that multiplication between the x and the y. So all of those things have to be done before the addition and subtraction. Therefore, each one of those things is its own separate entity that we call a term. You can see what I'm saying there. And there are 2 different kinds of terms. We have variable terms that contain, well, variables. And then lastly, we have terms that do not contain variables. They're not variable, and so we refer to them as constant. Now, within each one of these terms, we have a series of things that are multiplied together. And if you recall, multiplication is commutative. We can switch things around any way that we like and put things in whatever order we desire. And so, just in an effort to be as, well, OCD perhaps as possible, we place the numbers out front and we call them coefficients. And in addition to that, since the number is out front, we follow that up with the variables, and we tend to place the variables in alphabetical order. In this case, x followed by y. Now, we actually can take a look at some of these terms even when we have variables, and actually combine some of those together. And that becomes apparent when we take a look at these 2 examples on the left here. 4 apples plus 3 apples equals 7 apples. That's pretty straightforward. 5 bananas minus 2 bananas, well, what is that? That's 3 bananas. In the same way, 5x plus 7x, that's 12x. And 9y squared minus 6y squared is, you guessed it, 3y squared. So we can take some of these terms, even though they're sort of separate entities, and we can actually combine them together using these kinds of rules here. Here's another example. 15xy squared minus 7xy squared. What is that? You probably guessed correctly that it's 8xy squared, 15 minus 7. So let me ask you here, are these things like terms? Are we dealing with apples here? Are we dealing with oranges here? Or are we trying to combine apples and oranges here? Well, as it turns out, these are actually apples and oranges. We cannot combine these together. X squared y is makes it a different term than xy squared. In order for 2 things to be like terms, they have to contain the same variables and the same exponents on those variables. So here's an example of some terms here that might look a little overwhelming at first, but let's see if we can combine all the like terms that we see on this slide here. Well, I'm going to take a look at some of these, and I'm going to say, okay, here's 2y, and I can combine that with 7y, and 12y I'll place over there as well as 4y here. Okay, I think that's all the y's. In addition to that, let's place all the x's over here. I've moved negative x over there, and 10x, now 2x. And now let's take a look at all the xy's. There's 2xy, I'll put that with 8xy. I'll see about moving the 5xy over here, and that should be all the xy's. Let's also take the x squared y's and let's put all of those together. So there's 7x squared y being placed with 19x squared y. Oh, and also 5x squared y goes in that same area. Now there's xy squareds that I want to place together. So I'm moving that 6xy squared with the xy squared and the negative 3xy squared. And then we have that minus 9x squared y squared term there that pretty much stands on its own. And we can combine all of these terms together. Let's first of all combine the y's together. If we combine all of those, we get 2y plus 4y, that's 6y, minus 7y, that's negative y, plus 12y, that's 11y. In the same way, if we start to combine the x's together here, we can take negative x, add that to 10x, that's 9x, plus 2x, that's 11x. Let's take the xy squareds here and take xy squared plus 6xy squared, that's 7xy squared. Now we subtract 3xy squared, and that gives us 4xy squared. Moving over to the right here, we can take the 2xy and add that to 8xy, that's 10xy minus 5xy, that's going to give us just 5xy. Over to the lower right, we have 5x squared y plus 19x squared y, that's 24x squared y, and we add that to 7x squared y, that is a total of 31x squared y. And like I said, that last term there, negative 9x squared y squared, stands alone by itself. Now we define terms not only by their coefficients out front, the number out front, but there's something I want you to also be aware of here, is that we define something called the degree of the term. For the 11x, the degree is 1. For 11y, the degree is also 1. For 5xy, the degree is 2. We have two variables there instead of one, so the degree is 2. For 4xy squared, we have one x in there and we have two y's for a total of 3. The degree of that term is actually 3. In the same way, 31x squared y, there are two x's multiplied together there, and there's also a y multiplied there for a total again of 3. That's the degree of that term. Lastly, the negative 9x squared y squared, that has a degree of 4. Two x's and two y's. And the way that we tend to organize and display all of these terms together is we start with the highest order term. So that's negative 9x squared y squared here. And then we follow it up with the lower degree terms to follow there. So that's going to be 31x squared y and then 4xy squared. Those are the degree 3 terms. We have a degree 2 term here. That's the 5xy. So we put that one next. And then let's put in the degree 1 terms. That's plus 11x and then plus 11y. So it's just a nice way in which we organize all of this stuff and display it in a nice friendly order here. So identify the terms and coefficients that we have here. How many terms are there? Well, when I take a look at this, I see 4 different terms. The first term has a coefficient of 14, the second one negative 6, the third one 3, and the fourth one just 5. By the way, that 5 would be a degree 0 term. There are no variables in it, so its degree is 0. Now, how many terms is this? This is actually an important point here. As it turns out, even though there are 2 terms inside those parentheses, When we look at it from a bird's eye view, the way that we're doing here, that's 6 times the quantity x plus 1. That's two things being multiplied together. That's just one term sitting before us. The last operation there is multiplication. So we're dealing with two things that are being multiplied together. That's no different than 2x. Two things being multiplied together there. So that's really just one term. So how many terms is this? When I take a look here, that's negative 6x plus 5 times that monstrosity. That whole thing there is just one term. Minus 3y, that's another term, and plus 4x, that's the last term. So we have 4 terms here. We're also asking which one of these are like terms. Well, when I see negative 6x and positive 4x, those two terms have the same variable in it, raised to the same power of just 1. So those two terms are like terms, and those could be combined. So let's talk about some of the ways in which we can manipulate these kinds of things. What I'm really going to show for you or really describe for you things that you already know when it comes to mathematical properties. Some of these mathematical properties that you've actually worked with and have known for quite some time will define some legal dance moves as we manipulate these equations into whichever way that we want to have them. Here's the first one, the commutative property of addition. 3 plus 5 and 5 plus 3 gives you the same answer. The order does not matter when you're doing addition, which means that addition is commutative. We describe this algebraically by saying if we're adding two numbers together there, a plus b, we should get the same answer if we add b plus a. A plus b equals b plus a. That's a template way of describing the relationship that exists between two numbers that are added together one way and added together the other way. You can see some examples of that. Negative 4 plus 7, that's the same thing as 7 plus negative 4. We can switch those things with addition. We can also do it when we don't know what the number is, like x plus 3. We don't know what x is, but we know that we can switch those two things there to 3 plus x. So that's a legal dance move as we are manipulating these expressions and equations. Something else is also commutative, and you probably are also aware of this. 7 times 5 is 35. 5 times 7 is 35. 3 times 4 is 12. 4 times 3 is 12. Again, with multiplication, the order does not matter. And we can see that symbolized here with this formula here that says a times b. If you're multiplying two numbers together, you should get the same answer as if you're multiplying b times a. The order doesn't matter here. And you can see a couple of examples of this. Negative 5 times 9, same thing as if you take 9 and multiply it by negative 5. Again, we can do this even if we don't know what the numbers are. 8 times y, same thing as y times 8. So that again defines a legal dance move of being able to switch things when we're manipulating these expressions and equations. So it works only for addition and multiplication. It does not work for subtraction and division. So we can use these commutative property applications here for manipulating these 4 expressions here. 6 plus p, what can we do with that? Well, we can switch it to p plus 6. We can switch those two things around. In the same way, we can take negative 5 plus n, and we can switch that to n plus negative 5, which is the same thing, as you recall, as n minus 5. Subtracting something is the same thing as adding its opposite, so we can we're adding the opposite over here, so that can be also represented as subtraction. Next is y times 8, and that can also be expressed as just 8 times y. And lastly, x times y, well, we can switch those as well, so that they just say y times x. So that's the commutative property. Let's also talk about the distributive property. As it turns out, you also know about this as well. Let's say, for example, that I am packing lunches for 3 people. So I'm packing 3 lunches here, and inside each one of these bag lunches that I'm creating is a sandwich, just one sandwich, 2 hot dogs, and 3 apples. Maybe it's a day at Rocky Stadium or something for hot dogs and apples. So that's why it's such a big meal here. So the question here is, how many apples do I have to purchase? How many sandwiches do I have to buy? And how many make? And how many hot dogs do I have to make? Well, you probably can already figure out the answer here, but before you do, let me also represent this using an algebraic equation. I'm creating 3 of something. Well, what's that something? Well, it's in parentheses here. It's 1 sandwich, there's S for sandwich, 2 hot dogs, so there's H for hot dogs, and lastly 3 apples, so I have the letter A for apples there. Well, again, how much am I going to have to make or purchase for these packed lunches here? Well, as you've probably already been able to ascertain, I have to make 3 sandwiches, and I have to put together 6 hot dogs, and I have to purchase 9 apples. That's because your inner mathematician already understands the distributive property, that in order for us to make these 3 things put together, we have to multiply 3 times each of those quantities that are inside that package. We have to make 3 sandwiches, 3 times S. We have to put together 6 hot dogs, 3 times 2. And we have to purchase 9 apples, 3 times 3. We have to distribute that multiplication from that 3 on the outside there, on the very end, to each one of those terms. And so here's the way in which we describe this algebraically. Again, you already understood this. We're just finding a way to write it down using algebraic language. So let's say, for example, that we are putting together, we have these packages that contain B plus C. Who knows what those things are? That could be sandwiches and apples, or oranges and bananas, or something like that. But we're putting together more than one. The number that we're putting together is A, however many A is. So what's an equivalent amount of each one of those things that we're actually talking about here? As it turns out, we have to distribute that multiplication to each one of those terms. Just like before, we had to multiply 3 times the number of sandwiches and the number of hot dogs. We have to multiply A times B, and again, A times C. So you can see there a way in which we've described that. So we can see some examples of this. On the bottom we have -3, this also works with negative numbers, times the quantity 2 times x. Well, if we distribute that multiplication to both of those terms inside the parentheses, the first one is going to be -3 times 2, and the second one is going to be -3 times x. So that means that that first term is going to be -3 times 2, which is -6. The second one is just going to be -3 times x, or -3x. Here's some other applications of the distributive property here. 3 times the quantity x plus 4. Well, we distribute that multiplication by 3 to both terms here. That becomes 3x plus 12. We can also do this with some larger expressions inside of those parentheses. Here in this second example, we're multiplying by 2. 2 times 3y is 6y. 2 times -5z, that's -10z. And lastly, 2 times 1 is just 2. Here's another example. -8 times 2 minus 5y. So for the first term, -8 times 2. And here is one area where a lot of people mess up. There is a -8 that you're distributing to both terms there, and that second term is also negative. Make sure that that second term, that negative term there, also gets multiplied by that -8. You carry that negative sign in the -8 to both terms here. That means that that second term now is going to become positive. It's a -8 times a -5, that becomes a positive 40y. So our result here is -16 plus 40y. Sometimes what we're distributing is really just a minus sign. You can think of this as really multiplying something by -1, and so we're distributing that -1 multiplication to each one of those terms there. So the negative sign, taking the opposite of everything that's inside those parentheses, that negative sign distributes to each one of those terms there, effectively just changing the sign of each one of those terms there. So Negative 4a becomes positive 4a, positive b becomes negative b, positive 3c becomes negative 3c. Here's some more examples. I want you to see actually in this. Now here's something I also want you to see is that we've talked about combining like terms, and we've also talked about the distributive property here. And here is something I want you to see here, that when we're doing these things, they're actually the same thing, and one is actually the same thing in reverse of the other. If we took 8y plus 6y and we combine those like terms there, we would get, as you can see on the end there, 14y. Well, how did we get 14y? Well, you added 8 and 6 together. That's the middle part of that expression there. 8 plus 6 in parentheses times y. Well, here's what I want you to see here, is that if we go backwards to the left, notice that if I distribute that y to that 8 and distribute that y to that 6, in that middle section there, if I distribute that y to both of those terms, I can get back to where we started on the left here. I can get back to 8y plus 6y. Combining like terms and the distributive property are the same thing, one being the reverse of the other. Here's another example. 7x squared y minus 10x squared y, that's negative 3x squared y, but how did you get that? You took 7 minus 10. So 7 minus 10 in parentheses there in the middle times x squared y. Well, if we distribute that x squared y to both of those terms in parentheses, we can get back to where we started. Lastly, 15w plus 4w minus w. If we combine those like terms, we're going to get negative 12w. But again, how did you get that? You added negative 15 plus 4 minus 1, that middle portion there. All of that is times w. Well, if we distribute that w back to each one of those terms in parentheses, we can get back to where we started. Distributive property and like terms are the same thing. So let's put all of these things together here. We've got some legal dance moves that we can do. We've got the commutative property, we've got the distributive property, we can combine like terms. So let's try all these things here. We've got this expression, and what we want to do is use these dance moves to be able to simplify this expression that's before us here. So here's the first thing that I did. I made every place where it was subtraction into addition. Remember, subtraction is the same thing as adding the opposite. So where we had a minus 19, I made that a plus negative 19. And where there's a minus 10y, I made that a plus negative 10y. I made everything addition because I want to be able to use the commutative property to manipulate these things back and forth. So in this next part here, I'm just going to switch some things. I'm switching 8y and 4x, and again, I can do that. I can also switch these other terms here, negative 10y and negative 19. And again, I can do that because of the commutative property. Now, why would I switch those? Because those first two terms now are negative 3x and 4x. And so, as I have this now, I can combine those together into just 1x, or really just x. And 8y plus negative 10y, that's going to be negative 2y. And then I have plus negative 19 on the end there. Lastly, I can simplify this back again. 1x is just x, plus negative 2y, that's the same thing as subtracting 2y. And lastly, plus negative 19, that's the same thing as subtracting 19 there. So that's our final form. It's more simplified than the one that we started with. So again, we're using these legal dance moves to be able to simplify and manipulate all of these expressions that describe different patterns and relationships. So here's another example. We're given this expression here, and what are some things that we can do to simplify this? Well, here again, I want to point out that I don't know all the steps that are going to be needed in order to simplify this, but I do know what I could do next here. That's important to understand. You don't have to know all the steps. You just have to be able to look at something and say, well, this would make it better. And then once you've done that, well, this could make it better. And you just go through each one of those steps, and you eventually get to a place where you can't do any more, and that's simplified as far as you can go. So You don't have to know all the steps along the way, you just have to know the next step in front of you. And in this case, the next step in front of me involves using the distributive property to distribute that -3 to those terms in parentheses there. So I'm going to, first of all, oh yes, change the subtraction into an adding of a negative there. So that's going to be useful here. And now I'm going to distribute that -3 here to both terms. And I'm showing it kind of expanded here, just as a way of showing exactly what I'm doing in each one of those steps there. We still have the 6, but I'm taking that -3 and I'm multiplying it by 2y, and then I'm taking that -3 and multiplying it by 9. I'm just showing it really explicitly here, so don't be freaked out by the complexity of that. You're probably immediately able to take it from -3 times 2y, that's -6y, and -3 times 9, that's -27. So once I've got that, then I can switch the -6y and the 6 because of the commutative property once again, and now I can combine that 6 and the -27 together to give me just -21. So the final form here is just -6y minus 21. We've simplified that expression. Here's another example. What can I do here? Well, I'm noticing once again that we can use the distributive property to distribute each one of those, to basically get rid of all those parentheses there, and then we'll be able to combine those like terms, hopefully. So here's a way of describing it in a very expanded form here. The first thing I'm doing here is replacing the -4 inside of the first parentheses there with a plus -4. And so when I'm doing that, I want to show some square brackets around that x plus -4 there, just because there's parentheses there, and so I have to nest them using the square brackets. It's just parentheses inside of parentheses, so don't worry about the fact that there are square brackets there. Secondly, though, I've changed the minus 5x plus 7 to a plus -1 times 5x plus 7. And in this step, I'm showing very explicitly all of the operations involved in distributing that -8 to each of those terms, and also all of the operations involved in distributing that -1 to each one of those terms. It's probably more information than you need. Perhaps you're already at this point here, where -8 times x, that's -8x, -8 times -4, that's positive 32, and then we have a minus 5x and a minus 7. So we've done the distributive property successfully here. Now, what have I done here? Well, if you take a look at this closely, all I've really done is taken the minus 5x and the 32 and I've switched them. What's that? That's the commutative property. And now I've positioned things so that I can combine them, combine my like terms there. -8x plus -5x, that's -13x. 32 plus -7 is 25. And we're done. We've simplified this significantly to a point where it's just 2 terms. Now, you'll notice that I've been using the term expression quite a bit here. And there's a specific reason for it. It's very, very much on purpose. It's because the things that we've been manipulating here have not really involved an equal sign. We've been just dealing with sets of like terms put together with addition and subtraction and stuff like that. We haven't seen really an equal sign yet. And so that's why I've been using the term expression for it. It isn't until we take 2 expressions and we set them equal to each other that we have something that is called an equation. The smaller word inside of the word equation is equate or equal. It's describing very directly the presence of that equal sign there. And it's only when that equal sign is there that we actually have an equation. So a very simple equation would be something like this. An unknown x is equal to 7. It's pretty easy to see what x is at this point. It's obviously 7. And this might seem a little bit more than what's necessary here, but A way that you can check to see if there's a solution to an equation is to plug in a specific number into the variable to see if you get a true statement. So for example, I'm thinking, rather obviously, that the solution to this equation is 7, so I'm going to plug 7 in for x, and when I do that I get a true statement. 7 equals 7. That's always true. That means that 7 is the solution to that previous equation there, x equals 7. Now that becomes a little perhaps more challenging when we take a look at an equation like this, z plus 3 equals 8. Well, what's the solution to this? Well, I suspect that the solution to this is 5, so I'm going to plug in 5 for the variable here, and I'm going to simplify this, both sides of this, to see if I get a true statement. And of course, I do. 8 equals 8, that's a true statement, so 5 is a solution to this equation. Let me try it with this one over here as well. Negative 6p is equal to 18. I suspect that the solution to this equation is negative 3, so I'm going to plug that in here for p, and when I do that, negative 6 times negative 3 is positive 18, so once again, I do have a true statement. Negative 3 is indeed a solution to this equation. So here's a couple of examples here. 2x minus 9 equals 3, and I've separated off a number there that I'm suspecting is the solution to that equation here. Ignore the semicolon, it's just a separator between those two things. 2x minus 9 equals 3. I'm suspecting that the solution is 6, so I'm going to plug in 6 for x here, and I'm going to see if I get a true statement or not. Order of operations says that I should multiply 2 times 6 first. That gives me 12, and then I subtract off 9 to give me 3. I have a true statement. 3 equals 3. 6 is indeed a solution to that equation. Let's try the second one. Negative 2. I'm suspecting that that's a solution to the equation 20 equals 8p minus 4, so I'll plug that in for p. And using order of operations, 8 times negative 2 is negative 16. Negative 16 minus 4, oh, that's negative 20. So I'm getting a false statement here, which means that negative 2 is indeed not a solution to that equation. So take some time to do these two here. In this case, you're determining if those numbers after the semicolon are in fact a solution to each one of those equations. Take some time for that. Welcome back. Well, we see two examples here of the process of determining whether or not a given number is a solution to an equation simply by plugging in that number in for the variable. And we see for the first one that 7 is indeed a solution to the equation 2 plus 3x equals 23. And for the second part, 2 is in fact not a solution to the equation 9 equals negative 4x plus 1. Let's go back to our equation x equals 7 here, and I want to draw a picture here for you. I want to compare the equation really here to a scale. in which we've got, and it's specifically the kind of scale that has two pans to it, that the goal of which is to keep those pans in balance. And so if I've got an unknown weight sitting on one pan, the weight that I don't know what the weight is, but if I have 7 pounds sitting on the opposite pan and the pans are in balance, I know what the weight is of this unknown weight. It must be 7 pounds. And so I want you to be able to see the scale whenever we're drawing this equation here. So here's an example here. If I have a scale that's got 50 pounds on both pans here, it's obviously in balance because of that, and I add the same amount of weight to both sides, will the scale still be in balance? Well, hopefully you can see that in fact, yes, it will still be in balance. It'll now have 70 pounds on both sides. So I can add the same weight to both sides of a scale and still retain the equality, still retain the balance on both sides. In the same way, I can also take off the same amount of weight from both sides and still retain the equality, still retain the balance from both sides of the scale. So in the same way, if I've got some equation, A equals B, two things that are in balance on the scale, A and B, and A could be any of those expressions that we've seen in previous slides here, and B could be any of the expressions that we've seen in many slides long past, and if they're set equal to each other, if I add a quantity C to one side of the equation, so that I now have A plus C, well, what has to happen to the side that has B on it? Well, I have to add the same quantity, C. I have to add the same amount to that side as well in order for it to still stay in balance, in order for equality to be preserved. This is the addition property of equality. In the same way, I can also take off the same amount of weight from both sides of the scale. So if I have an equation, A equals B, in which A and B are any of those expressions you've seen previously, and I take off a certain amount to one side so that A becomes A minus C, then B has to now also become B minus C. I have to take off the same amount to the other side in order to retain equality. So here's some examples in which we can use this additional dance move to get these equations into a form in which the solution becomes obvious, namely into a form in which the variable is just by itself. Here's one that is x minus 6 equals 18. Now you might be able to already ascertain that the solution to this is 24. So yeah, 24 minus 6 equals 18. So that's great if you can do that. So this might seem a little bit more than necessary for finding solutions right now, but it's going to become absolutely necessary as these things become more and more complex. So bear with me on this, and just notice that I can add 6 to both sides of this equation, and if I do that, then the subtraction of 6, or the adding of a negative 6, cancels out with the addition of 6, effectively making it so that those two things really add up to 0, and adding 6 to the other side changes the 18 to a 24. So by adding 6 to both sides, I've effectively made the x by itself, and I have the solution sitting on the opposite side. X equals 24. 24 is the solution to this equation. In the same way, I've got negative 12 is equal to x minus 7. If I add 7 to both sides here, then I can make it so that the minus 7 goes away. Minus 7 plus 7, that cancels each other out. And on the left-hand side, I'm adding 7 to that minus 12 so that we have a minus 5. Negative 5 is the solution to that equation. So make use of this same technique with these 3 problems right here. Take some time to do that. Welcome back. Well, I'm showing a lot more work here than perhaps you did as you were solving each one of these things. The solution to the first one there was y equals 16. What I'm doing in those extra steps below is I'm checking to make sure that that is indeed the solution to that equation by plugging 16 into y minus 4 equals 12. And you can see that when I plug in 16 there, I get a true statement, 12 equals 12. So I'm doing the same thing for the other two problems here as well. For the bottom one, just to the left of me here, w is equal to negative 23. We got that by subtracting 5 from both sides of the equation. And then we can plug in negative 23 here in for the variable sitting on top. And we have negative 18 is equal to negative 23 plus 5 rather. And so we have when we simplify that, that becomes a true statement there. Negative 18 equals negative 18. Lastly, above me is negative 9 plus z equals 2. By adding 9 to both sides, that becomes z equals 11. And we can test that solution by plugging it into the original equation. Negative 9 plus 11 is 2. 2 equals 2. So we've got definitely a confirmation there that we have the right answer when it comes to the solution of those three equations. Here's just some more examples here. I'm going to allow things to become a little bit more complex here. On the left-hand side there, we've got a couple of like terms that can be combined, and also on the other side of the equal sign there, we have 12 minus 9. Those are like terms that can also be combined as well. So 3x minus 2, well, and my animation here is all messed up here, so I'll just show all of these at once. So negative 8 plus 3x plus negative 2x, so I'm making everything addition here, is equal to 12 minus 9. I can combine the 3x and the negative 2x to just get x on the left-hand side, so now it's negative 8 plus x is equal to 12 minus 9, which is 3. And if I add 8 to both sides, then that becomes just an x on one side and an 11 on the other side. In the same way, for the one directly above me, negative 5 is equal to 2 times the quantity y plus 1 minus y. And I can distribute that 2 to both those terms in parentheses to give us 2y plus 2 minus y. Well, I can combine the 2y and the negative y together to just get y. And if I subtract 2 from both sides of the equation, I get negative 7 equals y. So you can see that there's a sequence of steps to follow here. And again, I don't always know what steps I'm going to take in order to get to the solution. I just know what step to take next. And so if you can just keep it to that point where you know what step to take next, you're home free. So in the same way, work on these two problems here. They're a little bit more complex than the ones that you had before, but take some time to solve these two equations for their variables. Welcome back. Well, just like before, the actual solutions here are shown in boldface. Y equals -20 and x is equal to -13. The stuff that I do below each one of those solutions is actually plugging that variable back into the original equation to confirm that we have a true statement and that we actually have found the correct solution. So coming back to our scale here, I've got a scale that's in balance. There's 50 pounds in each one of those pans, and it's obviously set to balance each other. Now, if I triple the weight on both sides of this scale here, obviously the weight should still stay in balance. The scale is still in balance. Equality is preserved. And in the same way, if I cut into thirds, well, remove all but a third of all the weight that's on either side of the scale here. Once again, equality is preserved and the scale stays in balance. What does this say? If I multiply both sides, if I multiply the weight on both sides of this scale by the same quantity, the scale will stay in balance. And if I divide both sides of the weight that's on both sides of the scale here, again, the scale will stay in balance. In the same way, if I have an equation here in which I have A is equal to B, and I multiply A by something here, C, who knows what it is, the equality is still true if I also multiply the other side, B, by the same quantity, C. So if I can multiply both sides of the equation by the same quantity, C, and the equality is preserved. In the same way, if I have an equation A equals B, then if I divide one side of the equation by C, and I've indicated like directly above me here that C cannot be 0, we can't divide by 0, so C is not equal to 0, the equality is preserved if I also take B and divide it also by C. So I can divide both sides of the equation, of any equation, by the same amount, and the equality is preserved. So we can use that to simplify these equations right here, 10x equals 50. Now beforehand I had you taking an equation that said, let's for example, said x minus 5 equals 2. And on the left-hand side, you were trying to get the variable by itself. X minus 5 equals 2. Okay, well, I have to add 5 to both sides in order to get x by itself there. I had to do the opposite of what was being done in order to cancel that out and get the variable by itself. In the same way here, the variable in the first equation here is being multiplied by 10. And so we have to ask, what is the opposite of multiplication? Well, it's division. So instead of multiplying by 10, I want to divide both sides by 10 so that I can undo that multiplication here. Dividing both sides by 10. On the left-hand side, you can actually see it as two common factors in a fraction that can be canceled top and bottom here, leaving us with just 1x, and on the right-hand side, 50 divided by 10, that's just 5. So x is equal to 5. In the same way, we have p in the middle equation being multiplied by -4. The opposite of multiplication is division, so we divide both sides by -4 in an effort to get p by itself. We have p is equal to -7. Lastly, we have y being multiplied by a -1. That's negative y. That's not y by itself. We need to get it completely by itself. And so we can see that negative sign as being perhaps a multiplication by a -1. And we can divide that off by simply dividing both sides by -1. And the result is that we get y, positive y, now equal to -34. In the same way, we've got in this first equation here, x divided by 2 equals 6. The opposite of division is multiplication. So in this case, we multiply both sides of the equation by 2. And that, as you can see from my animation here, will cause those 2's to cancel out so that we just have x on that side here. 6 times 2 on the other side is simply 12. And in the middle one, x divided by 4. If we multiply both sides of the equation by 4, you can see here, what I'm really doing here is I'm showing fraction multiplication here. 4 divided by 1 times x divided by 4. Remember, you can cancel factors that are top and bottom before doing the multiplication here, so we can cancel those two 4s, one that's in the numerator, one that's in the denominator. All we have in the top now is x, all we have on the bottom now is 1, so that's just x. X is equal to, on the right hand side, negative 5 times 4, or negative 20. Lastly, on the right hand side here, we are undoing that division by negative 8 by multiplying both sides of the equation by negative 8. And again, that removes the negative 8 from that side, and on the left hand side we have negative 16. Negative 16 equals t. So here again, now we're using the multiplication and division properties of equality to help solve some of these equations. So work on these three here. In this case, you're undoing some multiplication to get the variable by itself. Take some time for that. Welcome back. Well, in the first equation here, we were dividing both sides by 4 to get the x by itself. We get an answer of x equals 8. In the middle one here, we are getting the w by itself by dividing both sides by negative 2 to give us w equals negative 9. And lastly, we're getting the m completely by itself by dividing both sides by negative 1 to give us m equals negative 19. Also work on these two here. In this case, we're not undoing multiplication, but we are undoing division. Take some time to do that. Welcome back. Well, in this instance, we were undoing a division by 6 by multiplying both sides of the equation by 6 to give us a solution y is equal to negative 18. And for the second one, we're getting w by itself by multiplying both sides of that equation by negative 10 to give us a solution w equals negative 50. All right, so let's just make these things a bit more complex. They might look a little scary, but really all we're doing is just the exact same dance moves to simplify and solve each one of these equations here. Let's start with the one on the left here. And for this one, notice what I'm doing first here. Ask yourself, what did I do? Well, in this case, I took 20 and 8, and I combined those together to get 28. In the same way, on the right-hand side, I took negative 10t and 3t. Those are like terms that I can combine to give me negative 7t. And now I want to get t by itself by undoing that multiplication by negative 7. So I'm going to divide both sides of the equation by negative 7 to give me t is equal to negative 4. In the same way, what am I going to do with this right-hand equation? Well, if you take a look at it, you might get some ideas of some ways in which you can simplify this. That negative 4 and the plus 10 can be combined. Oh, there's a set of parentheses that we can distribute that 3 over and make it so we don't have parentheses any longer. So as you're looking at these, start to notice ways in which you can do these kinds of dance moves to simplify what you've got here. So take a look at what I did there. What did I do? Well, hopefully you can see that I did the second of those two suggestions by distributing that negative 3 to the t plus 2 to give us negative 3t minus 6. Don't forget to distribute the negative 3 to both of those terms. And so both of those terms now should be negative. Negative 3t minus 6. What did I do here? Wow, that was just a big change here. Well, I combined the negative 4 plus 10 into just 6. And on the right-hand side, 4t minus 3t, that's just 1t. And lastly, negative 6 minus 1, that's negative 7. Wow, that's a lot more simple. Lastly, I can get t by itself by adding 7 to both sides, the result being 13 equals t. So in the same way, take some time to just solve this equation here. Take some time to do that. Welcome back. Well, this involved the distributive property, combining like terms, as well as adding the same thing to both sides of an equation. The result being that w equals 23. Now, what do we do when we're dealing with fractions and decimals here? Well, it's actually the same set of procedures. In this case, we have 9/4 is equal to q minus 3/4. Well, here the procedure for getting q by itself is exactly the way it's always been. We're subtracting 3/4, so the way that we undo that is to simply add 3/4 to both sides. That causes things to cancel out. On the right-hand side, we're left with just q. And on the left-hand side, we have 9/4 plus 3/4. That's just 12/4. And 12/4 is the same thing as just 3. In the same way, we can solve an equation that's above me. Z negative 1.2 plus z is equal to 4.6. Well, if we add 1.2 to both sides of this equation, then z will be completely by itself on the left-hand side, and we'll have 5.8 on the other side. We've solved that equation as well. In addition, what do we do when we're dealing with not addition and subtraction of fractions and decimals, but with multiplication by decimals here? How do we work with that? Well, in this case, we have negative 2/9 q is equal to 1/3. Well, if this were not a fraction, let's say if it were 2q equals something, the way that we would deal with this is by dividing both sides by 2 to get q by itself. Now this isn't just 2, this is negative 2/9, but the procedure is still the same. We want to divide off that negative 2/9. And how do we divide off negative 2/9? Division is the same thing as multiplication by the reciprocal. So instead of dividing by 2/9, we are going to multiply both sides by negative 9/2, the reciprocal of negative 2/9. Notice that on the left-hand side that results in a veritable cancel-palooza here of 9s and 2s, leaving behind just q. And on the right-hand side, we multiply those two fractions together. There's a cancellation of the 3, and, well, the 9 up there becomes a 3 when we cancel it with the 3 in the denominator, the result being just negative 3/2. So the result there is q is equal to negative 3/2. We can also get z by itself in the equation above me by simply dividing both sides by negative 0.7, and the result there is simply going to be z equals 4.9. So take some time with these equations here, one in which you're working with addition and subtraction of fractions, the other one in which you're working with addition and subtraction of decimals. Take some time to do that. Welcome back. Well, I gave you a fraction problem that was a little more challenging than the one that I had to do. You had to find a common denominator on the left-hand side in order to be able to add those fractions together. In this case, you can see we added 2/3 to both sides. 1/4 and 2/3, the common denominator of choice, is 12 there, and so 1/4, that's the same thing as 3/12. 2/3, the same thing as 8/12. The sum total being 11/12. That's a solution for the left-hand side there. For the right-hand side, we added 8.1 to both sides to get us 19.6. Let's also take some time for these two problems here. In this case, we are first multiplying a by negative 2/3 there. So how do we undo that multiplication? Think about the reciprocal technique that I gave you earlier in how to solve that. And also we've got the equation involving decimals directly above me. Take some time for that. Welcome back. Well, in this case, for the first problem, we got a by itself by multiplying both sides of the equation by negative 3/2. That's the reciprocal of negative 2/3. The result being a is equal to negative 3/8. And on the right-hand side, we got w by itself by dividing both sides by 2.2. The result being w equal to 3.1. Now let's also talk about how we translate English, basically English, into the appropriate language for math, which is algebraic language. And so let's do some examples of this here. The quotient of a number and 4 is 6. Well, the word quotient actually means division. So the quotient of a number, that's an unknown, so that means a variable. We're going to choose a letter to represent that. The quotient of a number and 4 is 6. Well, the quotient of a number and 4, that's x divided by 4. I've chosen x for our variable here, is 6. Well, that's equals 6. So you can see that we've translated that into x divided by 4 is equal to 6. And we can actually solve that for x by multiplying both sides of the equation by 4, and we have our solution x equals 24. In the same way, we can take a look at the second problem here. The product of a number and 4 is 6. Product means multiplication. So this is talking about the multiplication of a number, okay, that's another variable, and 4, so this is going to be x times 4, or 4x, is 6. 4x equals 6. And here we can solve this equation by dividing both sides by 4, and the result is simply 3/2. Similarly, we can translate these sentences in the same way. Negative 12 is equal to, all right, well that's pretty easy. Negative 12 is equal to the sum, sum means addition. The sum of negative 5 and a number, once again, and a number, that's a variable, something we don't know. So we're adding negative 5 and x. That's the other side of our equation here. So negative 12 is equal to negative 5 plus x. And we can actually solve that equation there by adding 5 to both sides, the result being x equals negative 7. On the right-hand side, the value 1.4 subtracted from a number. Now, we have to stop here for a moment here. The value 1.4 subtracted from a number. You have to watch subtraction and division pretty closely because there's two ways in which subtraction and division can be described. In this case, the value 1.4 subtracted from a number. Well, the temptation here might be able to say, well, that's just 1.4 minus x. 1.4 is first and then subtracting x from that. But for example, how would we say the value 2 subtracted from 5? Would we write that as 2 minus 5? No, we would write that as 5 minus 2. In the same way, the value 1.4 subtracted from a number, that's actually x minus 1.4. So there are times in subtraction when we're actually reversing the order of things in our language. The value 1.4 is subtracted from a number. In the same way, this also pops up in division because there are two ways in which we can describe division. Something divided by something, let's say 18 divided by 6 is 3. We can also describe that by saying that 6 divided into 18 is 3. So that's the reverse description of the same problem there. Divided by and divided into, or goes into, we have two different ways of describing division, and sometimes the way in which we're describing it requires a reversal of the algebraic language. In this case, the appropriate written description there is x minus 1.4 is 5.7. We can solve that by adding 1.4 to both sides, the result being 7.1. So make use of those skills here as you're translating these bits of English into algebraic language. Take some time for that. Welcome back. Well, hopefully this was pretty straightforward here. The sum of a number and 6 is negative 20, so x plus 6 equals negative 20. We solve that to get x equals negative 26. Second of all, 13 is equal to 5 subtracted from a number. There's that reverse description of subtraction there. So 13 is equal to x minus 5 in this case. We solve that to get x equals 18. Let's take some time to do these problems as well, these involving both multiplication and division. Take some time for that. Welcome back. Well, hopefully these were equally straightforward. The quotient of a number and -2 is 8, so x divided by -2 equals 8. We solve that to get x equals -16, and the product of a number and -3 is -24, so that's -3x equals 24. We solve that to get x equals 8. We've dealt with equations that are fairly simplistic, actually, in many of their solutions here, but I want to start to get into how do we solve multi-step problems. What do we do when we not only have to divide both sides of an equation in order to get a variable by itself, or add something to both sides to get an equation by itself, or subtract or multiply. Suppose we have to do more than one of those things in order to be able to get a variable by itself, not just one. Suppose it's more than one of those things. In this case, we have to be aware of which thing is undone first and which thing is undone next. And the way that we keep this in mind is to, for example, take a look at this first one. 2x minus 3 equals 15. Now, in getting this x by itself here, we're going to have to undo some multiplication. We're also going to have to undo the subtraction. But which do we do first? The answer lies in order of operations, but order of operations in reverse. Let me show you what I mean here. If I plugged in something for x, say 8 or something, and I wanted to evaluate that expression there, 2 times 8 minus 3, what do I do first? I do the multiplication first. That's the center of my onion. That's the first thing that I'm doing there. And it's only secondary that I then subtract 3 from that. That's the outermost layer of my onion. Since it's the outermost layer of my onion and the last thing that I've done, it's actually the first thing that I have to undone. It's the first thing that I have to peel off in order to get the variable by itself here. So the first thing I have to do here is to add 3 to both sides. I'm peeling off that top layer of the onion here. And the result is that I get 2x is equal to 18. It's now that I can divide both sides by 2 and get it down to the point where we have x by itself. X equals 9. In the same way, up here, the outermost layer of the onion is not the multiplication by -3. It is the addition of 10, which needs to be undone by subtracting 10 from both sides. The result being -3c is equal to -33, and we divide both sides by -3, and we simply get c is equal to 11. So the thing that we do last in order of operations, we have to undo first when we're trying to get a variable by itself. Let's do the same thing here with some of these other problems here. In order to get y by itself in that first problem there, we're going to have to undo the division. We're also going to have to undo the addition there. But the first one we're going to have to undo is that addition. So we're going to subtract 8 from both sides. That'll give us y divided by 2 is equal to 6. Now it's straightforward to see what we do next. We multiply both sides by 2, and the result is simply y equals 12. Now, the one that's above me is probably showing you something that I haven't shown you before. We've got x's on both sides of the equation. That's a little crazy, especially since we want to get x by itself. How do we do that if we've got x's on both sides of the equation? Well, the answer is that what we want to do is add 2x to both sides. We could just as easily subtract 4x from both sides. But the important thing is to make the x disappear from one side of the equation so that it's just on the other side. So if we add 2x to both sides here, it's going to disappear from the right side, isn't it? And it's going to only exist on the left-hand side. We've combined those like terms, 4x plus 2x, to give us 6x. So our equation is now 6x plus 5 equals 13. What do we undo first? The addition. We subtract 5 from both sides, the result being 6x is equal to -18. We can now divide both sides by 6, and the answer is simply x equals -3. So we can summarize some of these steps that we've come up with as far as solving all of these algebraic equations. And there's a place on your activity sheet in which I've given you some room to copy down each one of these solution steps here. You might have to actually pause the video a little bit in order to be able to take care of all that. But let's go through each one of those solution steps here. The first thing that we did really was we simplified either side of the equation using steps like clearing parentheses, using that distributive property to clear those parentheses, and then after that perhaps combining some like terms. And then after that's done, we add or subtract things to both sides of the equations to get all the variable terms on one side and all of the numeric terms, the constant terms, on the other side. Once we did that, then we use the multiplication and division properties of equality. We multiplied or divided both sides of the equation by something in an effort to finally get that variable exactly by itself. And once we have that, then we have x equals something, or y equals something, or the variable equals something on the opposite side here. We have a solution, and we can actually check our answer again by taking that solution and plugging it into the original equation to ensure that the solution is correct. So use these steps here as we are solving each one of these equations. Take some time for that. Welcome back. Well, hopefully this served as some good exercise for solving these kinds of equations that involve really two steps in order to get the variable by itself on one side of an equation. So 3x plus 7 equals 25. We subtracted 7 from both sides. We got 3x equals 18. Dividing both sides by 3, we have x equals 6. For the middle one, we subtracted 13 from both sides to get negative 25 is equal to negative 5t. And dividing both sides by negative 5, we have t equals 5. Lastly, on the right-hand side, we subtracted 9 from both sides to get x divided by 3 is equal to negative 12. Multiplying both sides by 3 gave us x equals negative 36. So take some time for this one here. I've kind of given you a challenge problem here to spend some time on, I know it looks crazy and big, but it's really the same procedures that we've been doing all along. Take some time and have some fun. Welcome back. Well, the solution to this equation involved using the distributive property on both sides of the equation, followed by combining some like terms, getting the variables on one side of the equation instead of on both sides, and then subtracting, in this case, 5 from both sides to get x equals -7. Now you might have had a different set of procedures that you used to get to your solution, but your solution should be the same as what's shown up here. There are many different ways in which you can get to the same solution, but they should all get to the same answer. So let's also come back here now to how we translate some of these English expressions into mathematical statements. A number decreased by 7 is 12. Find the number. Well, a number, that's pretty straightforward. X decreased by 7 minus 7 is equal to 12. All right, well that's pretty straightforward as far as being able to create an equation from that, and we can solve that by adding 7 to both sides and getting x equals 19 as our answer. Here's another example here. The sum of a number and -11 is -15. All right, well, the sum, that's addition, the sum of a number and -11, the sum of a number and -11 is -15. So you can see there what the equation is. X plus -11 is equal to -15. And you can see what we do in order to solve that. We simply add 11 to both sides and we get x equals -4. Going to get a little more challenging here. 7 less than 3 times a number results in 11. 7 less than 3 times a number. Well, less than obviously indicates subtraction, and this is one of those instances in which it's that reverse notation. 7 less than 3 times a number, well, that's going to be 3 times a number minus 7. So 3 times a number, 7 less than 3 times a number is going to be 3x minus 7, results in 11. Find the number. All right, well, let's add 7 to both sides to get 3x equals 18. We'll divide both sides by 3 to give us x equals 6. So we've translated English into an algebraic equation, and we've solved that equation to get the solution. 2 times the sum of a number and 8 equals 38. Now, let's be careful with this. 2 times, okay, so obviously this is going to be 2 multiplied by something, but this is going to be multiplied by the sum. So it's going to be multiplied by a package. The sum of a number and 8, x plus 8. It's 2 times that package being equal to 38. So 2 times the sum of a number and 8 equals 38. That's the equation we're going to solve by first doing the distributive property to give us 2x plus 16, and then subtracting 16 to give us 2x equals 22, then dividing both sides by 2 to give us our solution of x equals 11. Let's take a look at this one. 40 less than 5 times a number is 52 less than the number. That's a big mouthful there, isn't it? So let's just take one portion at a time here. 40 less than 5 times a number. All right, well, that's the left-hand side of our equation here. So 40 less than 5 times a number. Less than indicates subtraction. This is one of those reverse subtraction problems here. So let's look at the second part first here. 5 times a number. All right, well, that's 5x. 40 less than 5 times a number. That's going to be 5x minus 40. Okay, so what is that? Well, it's 52 less than the number, x minus 52. So that's the equation we have to solve there. And we can do that by getting x on a single side here. We'll subtract x from both sides. We'll have 4x minus 40 equals negative 52. We'll add 40 to both sides to give us 4x equals negative 12, and we'll divide both sides by 4 to give us x equals negative 3. Twice the sum of a number and 6 is 2 more than 3 times the number. Almost sounds like a nursery rhyme. Twice the sum. All right, so we're multiplying something by 2, but we're multiplying a sum times 2. We're multiplying a package times 2. And that package is a number and 6. The sum of a number and 6. All right, so that's x plus 6. X plus 6, quantity times 2, is 2 more than 3 times the number. 2 more than 3 times the number. All right, well, 3 times the number is just 3x. 2 more than 3 times the number, that's 3x plus 2. So there's the equation we have to solve, and you can see I'm already showing the first step there of doing the distributive property. Then we get the x's on one side, so we have 12 is equal to x plus 2. We're almost home free here. Subtract 2 from both sides, and we get x equals 10. So work on this one here next. A number minus 32 is 3 times the number. Find the number. And then lastly, 4 subtracted from 8 times a number. 4 subtracted from 8 times a number is 7 times the number plus 1. Find the number. We'll take some time to do that. Well, welcome back. Here we translated a couple of English statements into some algebraic equations, and those got solved. So hopefully that was pretty straightforward there. Let me show you some interesting things that sometimes happen when you're solving some of these equations. Here I've got 2 times the quantity b minus 4 is equal to 2b minus 7. All right, well, let's try and solve this here. I'm going to do the distributive property on the left-hand side, and I'm going to get 2b minus 8 is equal to 2b minus 7. Okay. Well, I'm going to try to get the variables on just one side. Well, I'm going to subtract 2b from both sides, but that's going to do something a little odd. It's going to make it so that b's completely disappear, and all I have on one side is negative 8, and on the other side is negative 7. Those two things are never equal. Guess how many solutions there are to this equation? The answer is none. This is one of those equations that has no solution whatsoever. So we sometimes have a term for this. We call it a contradiction. This is an equation that no matter what number you plug in, you're going to get a false statement, never a true statement. In addition to that type of thing, let me show you this example of something that happens sometimes as well. Well, let's see if we try to solve this one. I'm going to use the distributive property again on the right-hand side, so that becomes 4k minus 6, and I can add those two numbers on the right-hand side to get 4k minus 5, and good gosh, I'm going to have to get those variables on one side, so I'll subtract 4k from both sides, and again the variables all disappear here, but this time I'm getting a statement that's true. Negative 5 is equal to negative 5. Well, guess how many solutions there are to this equation? The answer is an infinite number of solutions. Every number is a solution to this equation. I could plug in 0, 1, 10, 1,000, square root of pi. Whatever I put in is going to result in a true statement. So this has an infinite number of solutions. The solutions are all possible numbers. And we also refer to this as an identity. So once again, every number is a solution to this equation. We call this an identity. So with that in mind, solve these two equations bearing in mind that they might have 0 solutions or an infinite number of solutions. They might be a contradiction or an identity. Take some time for that. Welcome back. Well, the variables dropped out in that first equation to the left-hand side. They're giving us 3 equals 3. That's a true statement. Maybe you got a different statement at the end there, like 0 equals 0 or something like that. As long as you got a true statement, then your answer is the same as mine. All numbers are solutions. There's an infinite number of solutions. This equation is clearly an identity. Similarly, or perhaps not so similarly, when all of the variables drop out of the second one, we get something that's not a true statement here, in which case we have no solution. This equation is a contradiction. I want to talk a little bit more about fractions and how we deal with solving equations that have fractions inside of them. Now, I can solve this the way we did before, in which you can add 4 to both sides and then get a common denominator and add 2/3 and 4, and then you're going to multiply both sides by 3/7 to get rid of the 7/3 and all that sort of stuff. Or you can do something which I sometimes call the nuclear option, which is an effort to just get rid of all of the fractions in sort of one fell swoop. And you can do that by noticing that all of the fractions that are up there are thirds, have a 3 in the denominator. So if I multiply both sides of the equation by 3, then I can effectively knock out all the fractions after I simplify. But the hard part is doing all this simplification. So, for example, here's the first part here. I'm going to distribute that 3 to both terms there. All right, so 3 times 7/3, well, the 3's are going to cancel, leaving me with just 7x for that first term. Similarly, when I distribute that 3 to the 4, that's going to give me 12. So I'm going to have 7x minus 12. On the right-hand side, those 3's are going to cancel, leaving me with just 2. Isn't that nice and simple? We've knocked out all the fractions with one step, multiplying both sides of the equation by the denominator, 3. The result is 7x minus 12 equals 2, so we add 12 to both sides to get 7x equals 14. We divide both sides by 7 to get x equals 2. So it's a way of avoiding fractions by multiplying both sides by the denominator. But what do you do when there are different denominators? Well, what you do is actually something very similar to when you're adding 2 or 3 fractions together. You have to get a common denominator, and the way we choose the common denominator is to get the least common multiple of each one of those fractions there. And so in this case, we want to find the smallest number that all 3 of those denominators go into. We have 6, we have 4, we have 3. The smallest number that all of them go into is 12. So if we multiply both sides of the equation by 12, that's going to divide evenly each one of those denominators, making them all disappear. So let's distribute that 12 to the 5/6 x. Okay, well, that's a little bit complex, but when we do that, the 6 is going to cancel out with the 12. The 6 will become a 1, the 12 will become a 2. We're effectively canceling out a factor of 6 there. So 6 goes away, 12 becomes a 2, 2 times 5 is 10, so that becomes 10x. For the second one there, 12 is being multiplied by negative 3/4. The 4 cancels with the 12. The 4 becomes a 1. The 12 becomes a 3. And 3 times 3 is 9. On the right-hand side, 1/3 times 12. The 3 will cancel with the 12. The 3 becomes a 1. The 12 becomes a 4. The result, and actually I can show this here a little bit more elaborately here for you, 12 over 1 times 5/6. You can see there where the 6 interacts with the 12. The 6 becomes a 1, the 12 becomes a 2 when we cancel a common factor there. For the second one, 3/4, the 4 becomes a 1 and the 12 becomes a 3. We're canceling a factor of 4 there. For the last portion on the right-hand side there, the 12 becomes a 4 and the 3 becomes a 1. We're canceling out a factor of 3, top and bottom there. So the result is 10x plus 9 equals 4, and we can now solve this rather quickly. Subtracting 9 from both sides, we have 10x equals negative 5. We divide both sides by 10, and we get negative 5/10, or negative 1/2. But the important thing here is that we can knock out the fractions in one step by multiplying both sides of the equation by the least common multiple of all the denominators. So actually take some time to exercise that here by solving those two equations, all of which involve fractions. Now, for the first one there, think of what the least common multiple is of all those fractions, 5, 2, and 10. What's the smallest number that all three of those denominators go into? And similarly, for this second equation here, you have 4 denominators. What's the smallest number that all 4 of those go into? Take some time for that. Welcome back. Well, at first glance, this might look like a great big mess here, but if we take this step by step, then we can see exactly what was done here. And hopefully this strongly approximates what you did as well. For the first one, the least common multiple of 5, 2, and 10 is in fact 10. 10 is something that 5 and 2 and 10 all divide evenly into. So if I multiply both sides of the equation by 10, then I can knock out all those fractions. 10 times 2/5 y, well, 10 and 5, we're going to cancel out a factor of 5 here, so the 5 will become a 1 and the 10 will become a 2, so 2 times 2y is going to become 4y. 10 times 1/2, you're going to cancel out a factor of 2, so you'll have the 2 will become a 1 and the 10 will become a 5 rather. So once again, let me describe that again here. 10 times 1/2, that's 10 over 1 times 1 over 2. So 10 times 1, 10 on top. 2 times 1, 2 on the bottom. 10 divided by 2, that's just 5. So on the left-hand side, we have 4y plus 5. And then on the right-hand side, you can see pretty easily there that those 10s are going to cancel out, leaving you with -7. So if we add -5 to both sides, that becomes 4y equals -12. And if we divide both sides by 4, we get y equals -3. All right, so the one on the right here. For that one, the least common multiple of all of those denominators is 20. So 5 goes into 20 evenly, 2 goes into 20 evenly, 4 goes into 20 evenly, and 10 goes into 20 evenly. It's the smallest number that all 4 of those numbers go into. So 20 is the clear number of choice here, so we're going to multiply both sides by 20, and let's go through the cancellation process here for each one of them. 20 times 2/5 x here. So maybe it's a little easier for me to simply do the multiplication first and then do the canceling. 20 over 1 times 2/5. 20 times 2 on top, that's 40. 5 times 1 on bottom, that's 5. So 40 divided by 5, that's 8. 20 times -1/2, so 20 over 1. 20 times 1 on top, 1 times 2 on bottom, that's 20 divided by 2. 20 divided by 2 is just 10. Okay, so on the right-hand side, 7/4 times 20 over 1. 7 times 20 is 140. That's 140 on top, 4 on the bottom, and that's equal to 35. 140 divided by 4 is 35. And for the last one there, 3/10 x times 20. All right, so 3 times 20 on top, that's 60. 10 on the bottom, 60 divided by 10 is 6. So that becomes 6x. So our equation now becomes 8x minus 10 equals 35 plus 6x. And we can simply subtract 6x from both sides to make that 2x minus 10 equals 35. We add 10 to both sides to make it 2x equals 45. And we divide by 2 to get 22.5. Let's do some application of some of these equations here. The first one is something called simple interest. Interest is nothing more than something that you pay, it's money that you pay somebody else for the privilege of temporarily using their money. So in this case, there's a $1,000 investment in which you are giving somebody else your money, and they're actually going to pay you some interest for the privilege of them using your money. So you're investing $1,000 for 2 years at an interest rate of 6.25%. Now these interest rates are always made in association with a time frame. 6.25%, that's associated with a given frame of time. It's usually years, usually it's annual. So, and in fact, when you see on television, APR, that's annual percentage rate. That's the percent interest that you pay per year when you're purchasing, say, a car. So in this case, we have 3 things, and we're going to be calculating what the interest is on this $1,000 investment. Now the $1,000, that's your principal. That's actually P in the equation there. Principal, that's the amount that's being invested. Or if you're borrowing money, that's the amount that you initially borrow. So $1,000 is the principal. The rate is 6.25%. Make sure you express that as a non-percent, like a decimal or a fraction or something. As you put that in for R, that's what R is. And lastly, 2.5 years, that's what you put in for T. And so we can find out what the amount of the interest is by plugging all those 3 things in and finding out our interest is $156.25. That's the amount that you're going to get back in addition to your principal when you make that investment. Here's another example here. And in this case, we're not solving for I, we're solving for something else. And so we actually want to try and manipulate this equation a little bit so that it's more attuned to our purposes. Look at what's being said here. For a $2,000 investment, that's principal, over 5 years, that's time, someone paid $750 in interest. That's I. So we have principal, we have interest, and we have time. What's the one thing we don't have? That's R. We don't know what the interest rate is. And, interestingly enough, they're asking us what was the apparent interest rate that was made on this investment here. So take a look at this equation up here and ask yourself the question, even though these are all letters and none of them are numbers, is there a way in which I can get R by itself? Well, R is being multiplied by P, and it's being multiplied by T. So if I undo that multiplication by dividing by P and T, both sides of the equation, then I'll have R by itself. So let's actually do that. When we solve for r, we divide both sides by pt. When we do that, pt cancels out on the right-hand side, doesn't it? Well, it cancels out on the side where the variable r is. So PRT divided by PT, those P's and T's cancel, you just have R left over. We're dividing the other side of the equation by PT as well, so we have I divided by PT. We've solved for R. R is equal to I divided by PT, and now we can simply plug in all of those numbers and evaluate what we get here. The interest on top was $750. The principal on bottom was $2,000 over 5 years. The result is 0.075, which expressed as a percent is 7.5%. So those are some examples of some applications that involve interest. But even more significantly, you had some experience here with taking a formula, that is an equation that only has variables in it, and manipulating that formula as if it were some of the other equations that we had with just one variable. You can do these same operations, multiplying both sides, dividing by both sides, adding both sides, subtracting both sides, distributive property, all of those things, even if you're only working with variables. And you can do that to manipulate this formula into a form that really describes the same relationship, but in a way in which you can solve for something different. In this case, solving for the interest rate. Here's a different kind of application problem here, and this is actually true. I have two cats. Their names are Simba and Piper, both of whom are indoor and outdoor cats. When Simba is outside and Piper is inside, the litter box needs to be changed once every 6 days. When Piper is outside and Simba is inside, the litter box needs to be changed every 3 days. So how often will the litter box need to be changed if both cats are inside? Well, this is an interesting kind of problem, and one that might be somewhat puzzling as to how to address it first here. Well, is it 6 plus 3? Well, that's 9 days for both cats. That doesn't make any sense. So you wouldn't have to change it as often, only every 9 days. So obviously those two time periods don't add together when we put the two cats together. How exactly do we solve this kind of a problem? Well, here's some important things to consider here. When Piper is inside, the litter box needs to be changed every when Piper is inside, the litter box needs to be changed every 6 days. So how much of the litter box is she using up every day? The answer would be 1/6 of the litter box. It's kind of a disgusting picture, but nonetheless, that's true. Piper uses up 1/6 of the litter box every single day. Now, if Simba is inside, the litter box has to be changed every 3 days, so he's using 1/3 of the litter box every single day. So if Simba and Piper are at home together inside, then they're using 1/3 plus 1/6 of the litter box each day. So you notice that in going from the time frame to the rate at which they were using the litter box, that's a reciprocal process, isn't it? We went from 6 days to 1/6, and we went from 3 days to 1/3. So we went from a time frame to a rate. How much are they using each day? That's a rate, in contrast to a time frame of the litter box needing to be changed every 6 days or 3 days. So Simba and Piper use up 1/6 plus 1/3 every single day. Well, that means that they're using half the litter box every single day. And so you can probably ascertain from that point that if they're using half the litter box every single day, that means that the litter box needs to be changed every 2 days. But I want you to also notice here that that's the reciprocal relationship again here. We switched from 1/2 to 2. So we're switching from a rate using 1/2 the litter box a day to a time frame of the litter box needing to be changed every 2 days. Again, that's that reciprocal relationship here. It's important to keep that in mind for some of these later problems here. Here's an example. pipe 1 fills a tank in 6 minutes, and pipe 2 fills the same tank in 8 minutes. Let's say that both of those faucets are turned on and they're working together. How long does it take for both pipes together to fill the tank? Well, once again, we have time frames here. We can't really add those time frames here to describe what happens when those two faucets are working together. The time frames don't add, but the rates should add, shouldn't they? So we want to convert, once again, those time frames to rates. And again, that's a reciprocal relationship. So if pipe 1 fills the tank in 6 minutes, that means in 1 minute, pipe 1 will fill 1/6 of the tank, won't it? That's the rate at which pipe 1 is filling the tank. In the same way, in 1 minute, pipe 2 will fill 1/8 of the tank in that single minute. Those are the two rates, and those are the things that can add. And when I add those things together, 1/6 and 1/8, I get 7/24. So in 1 minute, those two pipes are filling 7/24 of the tank. It might be a little difficult to ascertain what does that mean as far as time frame is concerned, but remember, we have that reciprocal relationship here, and so even though it's a little harder to ascertain, the reciprocal relationship still exists. And so if we want to convert that rate back into a time frame, we do the reciprocal once again. So 7/24 simply becomes 24/7. That's how many minutes it takes for those two pipes to fill up the tank. 24/7 can be converted to a mixed number, 3 3/7 minutes. Well, that makes sense. If pipe 1 fills it in 6 minutes, pipe 2 in 8 minutes, then the two of them working together should fill it in a time frame less than either one of those. It should be less than 6 and less than 8. 3 3/7 minutes makes sense. So in the same way, work with this problem here. A faucet fills a sink in 8 minutes. A drain empties the sink in 8 minutes. So ask yourself the question, are those rates working with each other, additively, or are they working against each other, subtractively? So if both the faucet and the drain are open, how long will it take the sink to overflow? Take some time for that. Welcome back. Well, in this case, we have a faucet and a drain working against each other, and so those rates are going to subtract instead of add. In 1 minute, the faucet will fill 1/6 of the tank. The drain will empty 1/8 of the tank, and so those combined rates together will be 1/6 minus 1/8. And so in order to figure out what that is, we have to get a common denominator. 4/24 minus 3/24 is equal to 1/24. We have that reciprocal relationship to fall back on once again as we convert that rate back into a time frame. The sink will overflow in 24 minutes. Well, speaking of overflowing, this is a video that's covered a tremendous amount of information. So as you take a look at your activity sheet, there's a lot of stuff that we've covered here and a lot of things to perhaps annotate as you summarize the information that's here. We've gone through a lot of properties. The commutative property, where you can switch things that are addition, switch things that are multiplication. We've talked about the process of combining like terms. We've even defined what a term is and what those like terms are that can be combined and which cannot be combined. We've talked about the addition property of equality, the subtraction property of equality, the fact that you can add and subtract both sides of something to both sides of an equation. You can multiply both sides of an equation by something. You can divide both sides of an equation by something. In addition, we've talked about some techniques for translating English phrases into algebraic equations. We've also talked about some strategies that you can make use of as you are working with fractions, multiplying both sides of the equation by the least common multiple of all the denominators there. We've also talked about some example applications, like working with some of the rates, like we did in this problem here. Also some simple interest problems in which we worked on those together. There's a lot of information that we've covered in here. It's really the full introduction into algebra that we've covered in this video. So it's a lot of stuff. Annotate what you need to, and I'll see you in class soon.